Yes, hello everyone. My name is Edwina Solomon Spencer. I'm a student at Macquarie University doing software engineering. Yes, today in this video, I'll be talking about. It's a continuation of my previous video, uh, facial recognition in security, in the field of security. So let me just share my screen very fast and get straight into the presentation. So. So basically, it's just like we had talked about facial recognition in the field of security. This is just basically like I had said, it's a continuation of the previous video. So facial recognition AI in the field of security is becoming more and more applicable in the field. Like for example, identifying threats in the community. Facial recognition is being used at airports, in banks, in homes, on your phone, when you're trying to unlock maybe your phone. Yeah, your smartphone. So basically that is it. So I want to talk about a data set. Data set is a collection of various types of data stored in a digital format. Just like these are some of the examples of what a data set comprises of. Storage has text, maybe audio, videos, numerical data points, etc. So for our scenario, since we're looking at facial recognition, we shall mainly be focusing on the face, because it's what is stored in the database. It's what the artificial intelligence uses when it's trying to maybe grant access to an individual or a personnel. So just before I go, there is a GitHub link that I just placed here. You can just copy it the way it is and place it in your web browser. This is the dataset that I'll be using for my project, or for my facial recognition artificial intelligence project. So it has quite a good number of images and other features that we shall be seeing, and all these features can enable the project to be of a very good performance. So that's why I chose it, and it's quite simple. Yeah, and when I begin the code, I will let you know, and you will see how simple it really is. Basically, there are a few lines of code, and you have created an artificial intelligence facial recognition. So factors considered when choosing a data set above, I considered the size of the training data. It has quite a good amount of training data, and it is also it's good when you're also trying to get reliable predictions. When you're having small data, also the predictions that you get are, but if at all are limited. But if at all you're having quite a good amount of data, even the predictions you make, they are also quite they are not limited. So speed and training time, yeah, I think first of all, that data set that I just showed you, it has been there like for close to, is it 9 years? And each time it's just being what? Refurnished and making it much more better. So it has a good higher training time, and also the algorithms require more time to train large training data. Okay, so when you're trying to what I'm trying to make here is that the high accuracy typically means that the higher training time. So if at all your data set is good, you'll also be able to, even the training time, it's a good training time. You'll find that if at all you're having a very nice data set, even it doesn't need like a lot of training. So the number of features, hard cascades got quite a good number, or there's a typo. Good number of features that meaning that's much better performance. Just like I said, if at all you're having quite a good number of features, you're able to to do quite a good number of things. So even then, and in the end, you'll find that you have a better performance. So another factor is the accuracy. Accuracy, I talked about accuracy in my previous video, and we are looking at some of the true positives, true negatives, the false positives, and the false negatives. So all those are put into consideration also when you're trying to choose a proper data set. And also this. So that's why I'm saying that higher cascades predicts a value that is close to the true response value for that observation. One can easily understand how an individual predictor is associated with the response, while the flexible models give high accuracy at the cost of low interpretability. So you find that you may not have that the Haar cascades predicts a value that is close to the true response value for that observation. So because it has been trained and it's quite a good data set, and it has been so important features that a data set will use. So these are some of the various features this data set uses to distinguish between my face, your face, and all these faces. So the distance between the eyes, the distance from the forehead to the chin, the distance between the nose and mouth, all these others. So you find that with all these considerations being put into place, you find that there is what the rectangle. I'll be talking about the rectangle model, but whereby like a rectangle will be moving around a given face, and then it will have to store all those measurements, maybe the face, the eyes of this depth socket, the shape of the cheekbones, the distance between the eyes is such and such millimeters or something. Also, all those are put into consideration in trying to identify a face or store a face. So today I want to talk about some three new concepts. That is the Bayesian theorem, which is a method to determine the conditional probabilities. So basically here, you're trying to determine the probability after being given after knowing, for example, you're trying to determine A when you're given B. So that's why it's trying to say that the probability of one event occurring given that the other event has already occurred, because a conditional probability includes additional conditions. So in other words, more data. In other words, that means you'll have more data, so it can contribute to more accurate results. So in probability theory, it relates the conditional probability and marginal probabilities of the two random events. So these are some of the just let me show you something real quick. So this is the website I basically used, and it provides quite a good amount of information. Yeah, you can be able to get to know some of these differences between Bayesian theory, maybe naive, Bayes, and the rest that I'll be talking about at a later time. So, and you see, it also provides quite a good amount of all these languages, HTML, CSS, JavaScript, and all those. So it's quite a good website. Please, you can just copy the URL and you'll find all the content there. So back to the presentation. So basically, that's it. There's a simple explanation there. So Bayes' theorem, this is the formula. This is the formula that they use, and all these symbols. This is what they are mean. You find that this PA brackets A is the probability of the hypothesis H being true, and all the rest, as you can see from there. So naive Bayes is also a machine learning model that is used for like volumes of data. We know that naive Bayes basically used when having millions and millions of data. Trying to compute. It also provides very good results when it comes to the NLP and NLP tasks such as the sentiment analysis. So these are the three types of Bayes, and the website the website I shared earlier. This website can also help you to distinguish, and you can be able to know all those various types of what? All those various types of naive Bayes. So we have what we call a naive Bayes classifier, and it's a machine learning model segregating different objects on the basis of the certain features of variables. So you find that with naive Bayes, first of all, it looks at the features independently. You get so I'll be talking about that at a later time. It's a kind of classifier that works on Bayes' theorem, prediction of membership probabilities made on every class, such as the probability of data points associated with each particular class. So those are, you can just read through, and these are the hypotheses of the map, actually known as the maximum posterior. Yeah. So naive Bayes conclusion. So in naive Bayes, you find that the classifiers we find that all the variables or the features are not related to each other, just like I'm saying, that you find that it is considering them independent. So the existence or absence of a variable does not impact on the existence or the absence of any other variable. So for example, a fruit may be observed to be an apple if it is red, round, or about 4 inches in diameter. In this case, the naive Bayes classifier will observe all this independently, contributing to the probability that the fruit is an apple. So there is also a link here that I've put, and just gives us a more clear understanding of this naive Bayes. So Bayes networks is also known as the Bayes net, the belief network, or the decision network is a probabilistic graphical model that represents the sets of variables in their conditional dependencies. So basically, these are graphs. They just help you when you're trying to predict the likelihood of at any one of the possible known causes. So just let me repeat this. So Bayesian networks are ideal for taking an event that occurred and predicting the likelihood that any other of the several known causes was the contributing factor. So for example, the Bayesian network could represent the probabilistic relationships between the disease and symptoms. So given the symptoms, the network can be used to compute the probabilities of the presence of the various diseases. So basically here, let me just finish this and then explain. So they can be used for a wide range of tasks such as prediction, anomaly detection, diagnostics, automated insight reasoning, time series prediction, and etc. So this is the example that I'm going to explain. That if at all you're given that if at all you feel the symptoms of maybe various diseases, that these Bayes networks can be used to compute the probabilities that the presence of that amongst those symptoms is the presence of some various diseases. And the differences between the Bayesian and naive Bayes is that the conditional independence where it happens in naive Bayes, well, in Bayes theorem it does not. This means that the relationship between all the input features are independent, just like we have talked about. That in naive Bayes you find that all these features are independently looked at, unlike for the Bayes theorem. So also the difference between the naive Bayes and the Bayesian networks is that with naive Bayes, it assumes that the input variables are conditionally independent from each other, while Bayesian networks model the independences explicitly to give better prediction, just like we had said. That with naive Bayes, we find that we are looking at independent features, but then with Bayesian networks, we find that, for example, you've been given the symptoms and you're able to to detect the presence of various diseases. So these are some of the references. You can have a look at all these references so that you can be able to get a more clear understanding of what I'm trying to talk about. So see you in my next video. Thank you. Please, if you're tuning into this channel, I appreciate, I thank you. And please subscribe. Thank you. Have a nice day.